Okay, welcome to the Math Resource Guide for Decathlon. This is section 3.2, and it's going to be on basic limits and continuity. So before we can get into that, we need to discuss the slope of a graph. So the rate of change and the slope are the same thing, okay? So and then points on a straight line will always have the same slope because the rate of change is constant. For example, here we have, so if we go to this red line, right, we see that we are moving 1 unit to the right and 1 unit up. Now, if we use the blue line here, we're gonna be moving 3 units to the right and 3 units up. So the rate of change or the slope are the same because as you move 1 unit in the x direction, you're gonna move 1 unit in the y direction. Therefore, your slope is gonna be 1. Okay? And that's never going to change if the line is straight. But what is the slope becomes a more difficult question to answer when looking at something like a parabola, because the rate of change is always changing. So we can see that here when, well, as we go from 0 to 1, right, we're going to be moving 1 unit to the right and 1 unit up, which means our slope would be like 1, right? The rate of change is 1. But when we move from 2 to 3, we're actually moving up 3 points. So it's changing, right? You're moving up 1 unit, and now you're going to move up 3 units. And what that does is that it makes it so you can't actually find the slope at a single point. So, for example, we use this formula right here to find the slope of a line, right? So the y2 minus y1, x2 minus x1. It's just the basic rise over run formula. Okay? So if we try using this formula to solve for the slope on the parabola, it's going to give you different answers. So whenever you try putting in the point 1, 1, which is right here, it's not going to give you, and then, and also point 4, 2, you're going to get your slope as equal to 3. But let's say you keep using the same point, 1, 1, but then you're going to use the point 9, 3, you get the slope of 4. And obviously that's not the same slope, right? So clearly there's something going on here. And so what you can tell by this is that, well, you're not actually getting the real slope of the line, because you can get different slopes for the same point, and that doesn't make any sense. So you might think, oh, well, to find the point, or the slope of a line at a point, you just plug in the same point. But if we do that, we just get 0 over 0, and that's not very helpful. So you can see that over here. So what do? Well, in order to solve this, we're first going to have to understand something called limits. So limits are just the y value of a function as it approaches a certain x. So here, for example, in the first example, as we're approaching, so we're trying to solve the limit as x approaches 2. of the function, right? So let's go to x equals 2, and that's over here. Okay? So how do we solve this? How do we figure this out? Well, as we come in from the left, we are approaching a certain point. And as we come in from the right, we're also approaching a certain point, right? And in this case, it looks to me like the point we're approaching is 2, right? So the limit of x the limit as x approaches 2 of the function would be 2, because your y as you approach 2 is going to equal 2. So now let's try it with this next one. As the limit as x approaches -1, what is your y? So let's go to -1. That's right here, right? So we're going to come in from the top, okay? And you just draw a little arrow, see where it goes. And it looks like we're leading down to 0. And we'll do the same thing from the right. And we get what looks like to be 0. So your limit as x approaches 1 would be 0. So now for this next one, we have the limit as x approaches 1 of f of x. So let's just do the same thing. We're coming in from the right, or from the left, sorry, and we're drawing an arrow, coming in from the right, on the line, and it looks like we're at y equals 2. So the point would be 1, 2. But there's something funny about this one, right? Because whenever you are looking at the graph, you see that there's a point down here. So wouldn't it be that x, so the limit as x approaches 1 would be 1? Well, no, because just because the point is at a different spot does not mean that the function is approaching that point. So you always have to remember that the limit is not the same thing as the actual value of your y at that point. It can be a different number, like in this case. So just look at the graph and see as it approaches that point from both sides, that's going to be your limit. So in this case, the limit would be 2. Okay, so now we're going to look at limits at infinity. So for this first graph, right, we see it's just like a little parabola, right? So we want to find out the limit as x approaches infinity. So the way we do that is, well, we just follow the graph. Looks like as we approach infinity in the x direction, it looks like y is also approaching infinity. So what we would so the limit as x approaches infinity is also going to be infinity. Now, we're going to do the limit as x approaches negative infinity. So we'll do the same thing. We go up, follow the graph, and it looks like as we approach negative infinity is all the way down here, it looks like the graph, the y is going to be also positive infinity. Now, let's look at this next one. So we have the limit as x approaches infinity. So that's over here, right? So let's just follow the graph. It goes down like that. It keeps going. But what it looks like here that it's never, it's looking like it's evening out, right? At x equals 0. So we're going to say that the limit as x approaches infinity is 0. And now we're going to do the same thing for x approaches negative infinity. Again, we see the same thing. It looks like the graph is just about to hit 0, but it's never quite going to pass 0. So we're going to say the limit as x approaches negative infinity equals 0. Now for our last example, we're going to do the same thing. We're going to go across along the graph as we approach infinity, and it looks like it's evening out at y equals 2. So that's going to be our limit. And do the same thing at the bottom. It looks like it's evening out at y equals negative 2. So that's going to be our limit. Now, this is an example straight from the resource guide. So as we can see, so let's try and find the limits for this graph. So first we're going to do the limit as x approaches infinity. So we're going along, and it looks to me like it's evening out at 0. It's never quite going to pass that. So our limit as x approaches infinity is going to be 0. Let's do the same thing with negative infinity. It's going all along here, and it looks like it's evening out at 0, so our limit as x approaches negative infinity is going to be 0. Now, let's say I wanted to know the limit as x approaches 0. Well, if we follow along down here, it looks like the limit as x approaches 0 is going to be negative infinity, because it's just going up and up and up and up and up. So you might think to put negative infinity as your answer. But wait, look at the other side. As we follow along towards x equals 0, we go up and up and up, and it looks like it's approaching positive infinity. So what's going on? If it's negative infinity and positive infinity at the same time, that doesn't make any sense, right? So the way we are going to write this now is that we're going to do the limit as x approaches 0 from the left of 1 over x equals negative infinity, because as we approach from the left, again, we're going all the way down and down and down to hit negative infinity. And let's say the limit as x approaches 0 from the right of 1 over x, well, that's going to equal positive infinity, as we said earlier. So in order to solve a limit where the 2 points, the points that it's approaching are 2 different values, we have to split up the limits. We have to split it up into a negative, or from the left, and the right which is signified as a little positive right here. So to give you a couple more examples, I'll just draw a little graph right here. So let's say that this is a graph right here, and this is 1. This is x equals 1. So if we wanted to say, well, what's the limit of x approaches 1? Well, we follow it along from the left, and we get what looks like to be y equals 1. So we would write the limit as x approaches 1 from the negative, or from the left, f of x equals 1. And as we come from the right, we're going down, down, down over here, and it looks like it's at y equals 3. So we write the limit as x approaches 1 from the right of f of x equals 3. Okay. So the next thing that is interesting about this graph is that, well, it looks like there's no point at x equals 0, right? It's never quite going to reach, so these, the ends of the graph are never quite going to reach 0. So we say that x equals 0, there's no point at x equals 0, so we say it's x equals 0 does not exist, or we write it as dne. And this information is important in determining the continuity of a function. And in order to know if f is continuous, we have to look at the 3 following criteria. So the first one is is f of a exists. So there is no hole in the graph. There's no point in the graph that does not exist, right? There has to be a point in every single x. That's what this first one means. And then we have the limit as x approaches a of f of x exists. So the limit has to exist at every single point in the function. And then finally, for number 3, again, the limit as x approaches a of f of x has to equal the point of f of a. So basically that means the limit, so the limit of let's say x equals 1 has to be the same as the y value, the true y value of x equals 1. So we'll look at some examples. So for this first graph, we just have a line. It looks, so we're going to go through all the points. So is there any holes in this graph? Is there any point where it does not exist? Well, no. It looks like it's a solid line. There's nothing funky about it. Okay, so now let's go to point 2. The limit as x approaches a of f of x exists. So does the limit exist at each point? Well, it looks like it to me, because the limit, the only way the limit does not exist is if there's if it does not approach the same number from each side. So kind of like what we were talking about earlier. So in this case, if we would write So in this case, the limit as x approaches 0 technically does not exist because it does not approach the same point from both sides, right? So because it approaches negative infinity and infinity. So that's not happening right here. So let's move on to the next point, which is the limit as x approaches a of f of x equals f of a. So is there at any point in the graph, is there a limit in which the x or the point is at a different part of the graph? So it doesn't look like it to me because the line is there's no points that are outside of the graph, like down here or something like that. So it looks fine to me. So I'm going to say that this one is continuous. Okay, now let's look at the next one. Is there any point in which this graph, that we go through this graph, and is there a point that doesn't exist here? Doesn't look like it to me, so that one is good. There's no breaks in the graph. There's no point where the limit does not exist. Okay, so that one is okay. And the limit, so is there any point where there's like a point outside of the line? Is there something funky going on? No, doesn't look like it to me, so we're going to say that this one is also continuous. So now let's look at this third one. So, is there a point at every single x coordinate? Well, it looks like it to me because for every single x value you plug in, it looks like there's going to be some value that you're going to get. So that one looks fine to me. Now we have the limit. So is there a limit on every single one? Well, no. Actually, there's not, because if you look, as you approach from the left, you're going to get a different number than if you approach from the right. So this actually fails. So this is discontinuous because the limit as x approaches a does not exist. Okay, now we're going to look at this next one. So, is there a point at every single part of this graph? Well, no, it looks like there's a hole right here, right? There's no point at x, let's say this is x equals 2, right? There's no point there. And it's not like over here or anything like that, right? It's just gone. So we're going to say that this one is discontinuous because f of a or f of 2 does not exist. Now for our final one down here, we're going to look. So is there at any point in this graph a hole, right? There's a point that just doesn't exist. Well, no, because at every single x, you can plug in any single x and you're going to get a y value. So that one's not. So that one is okay. Now, does the limit of any point on this graph not exist? Well, it doesn't look like it to me because the only part that looks kind of weird would be this part, but as we approach from the left and as we approach from the right, they're both approaching the same number, which is infinity. So that criteria is okay. So now we're going to move on to the last part. Does the limit of each point on the graph equal the point, right? So this would actually fail because, as you can see, as let's say this is x equals 3, right? when x equals 3, the limit is approaching infinity, right? But we have a point down here at, let's say that's y equals 1, right? So infinity obviously does not equal 1, right? So this graph is going to be discontinuous because the limit as x approaches 3 does not equal x equals 3. Right? So that is just an example of each of the different ways it can be discontinuous. And that's it for today. The next section we're going to look at is section 3.3, the first derivative of basic polynomial functions and graphical interpretation. Thank you.